Okay, folks, well, we'll go ahead and get started. Let me go ahead and open us up in prayer, and I'll give you a sense of the things that we're going to be covering today. So, dear Heavenly Father, Lord, thank you very much for the chance to be working with each of the students in this course. I pray that the material will be clear. Pray that it is going to be helpful for them as they're looking to be completing their degree programs here at APU, and they can successfully get the job or company of their choice as they move forward. I also pray that you would help them in their spiritual formation, Lord, that you would help them to really see the value and really take it to heart that they are able to be studying scripture and deriving the theological concepts from that they can be applying in their life. Give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, what I'd like to do today is we'll go over chapter 8, input and output, and I want to make sure that I leave enough time towards the end. A little bit of show and tell. I have a couple of hard drives, so I'll just give you a chance to see what they look like. And then I also want to get into our Mars assembly language project and show you an example program in that I think might be helpful for you as you're starting to think about what comes next after your digital logic one. And so we've had a chance to be showcasing that. And next Thursday is when your digital logic is going to be due. And so that's the time where we can start to get some folks to share what they did on that. And I look forward to seeing that. Okay, well, let's get into chapter 9 and input and output. And so just maybe some context. We've been talking about the computer system, and we talked about the general nature of what a computing system is, fetch, execute. We then started to be thinking of memory in quite a lot of different ways, maybe some ways that you haven't even thought about that what's going on. And if there's a slight difference between the way that the instructions, how that is accessed to and from in memory, and the data. And so we got a chance to be seeing a little bit about that. We talked about locality, that we showed that this pyramid, that the closer you get to the CPU, you want it to be extremely fast memory, and so registers fall into that. We talked into this, maybe not exactly intuitive, how performance can actually improve when you have cache. And so we got a chance to be seeing what that is like. And then we looked at these two differences, the internal memory and external memory. And so we got a chance to be thinking about random access memory, for example, and some of the different types, DRAM, SRAM, and stuff like that. And then external memory, we got a chance to be thinking about hard drives, SSDs, and stuff going beyond that. Now we're going to be thinking more specifically just on the input and output. So we're not focusing on memory, we're focusing on getting information out, getting information to come back. And so these are the ways of how we're going to be getting our perspective on that. We'll be thinking about external devices. How do you get a chance to communicate and pass information with your keyboard, your mouse, your monitor? We have things like that. We'll be talking about in general, what is an input and output type of module. So this is a third area in a von Neumann architecture that we need to figure out exactly how that works. There's different ways that we can be doing I/O. We can doing programmed. So basically you daisy chain sample. Do you have anything? Do you have anything? Do you have anything? And it's either yes or no. It's not the most efficient way of doing things. Another possible way is an interrupt driven I/O. So basically you signal to the CPU, I have something that I need to have your help taken care of. And there's going to be some kind of a priority scheme that will determine not only who came first, but what level of priority it is. Another option is you can have direct memory access. So it's like the CPU says, okay, you're going to do this. I'm going to be standing idle while you do this, and I don't have to be involved in this exchange of information. That's possible. In addition to direct memory access, there's something called direct cache cache access. So you don't have to reach into the innards of the memory. If it's stored in cache, it can actually make performance go a little bit faster. We'll talk about channels and processors, and we'll get a chance to be thinking about a couple of different chips. We'll go into a little bit more detail about that. And so I think that'll give us a nice round overview of what I/O is all about. So here is a generic model of an I/O module. And so you have your address lines, your data lines, control lines. All of those have to be the interface of what an I/O module has. And so the interfaces come together, and this is the translator that goes from how you get information from the peripheral to the backplane in your motherboard to the system interconnects. And those are the three categories: address lines, data lines, control lines. All those need to be played out and worked out, and everybody's agreeing to the same interfaces and how you're handling that. So for external devices, it provide a means of exchanging data between the external environment and the computer. And so this is how you get a chance to access the external world from your computing system. You can attach to a computer by a link to an I/O module. This link is used to exchange control, status, and data between the I/O module and the internal device. You can have a peripheral device, an I/O interface device connected to an I/O module. A computing system would not be very useful if it didn't have a way to engage with the external world. It does something, it then needs to be communicating in a way that is useful, and we can take the next step. So there's three categories that we want to be thinking about. Human readable, so something that shows up on your monitor, like what I'm doing with these lecture notes here. So it's suitable for communicating with the computer user. You can have a video display terminals, printers, and things like that. You could print it out as well as having it on a display. You can have machine readable, and so it's suitable for communicating with equipment. And so you don't have to be reading it, but going from one piece of equipment to another. You can have a magnetic disc, a tape system, sensors, and actuators. So we'll get a chance of seeing this a little bit as we get a chance to be playing with our Arduino kits. Finally, communication. This is suitable for communicating with remote devices such as a terminal, a machine readable device, or other computer. So here is an illustration of an external device. And so it needs to be made so we can actually communicate with this I/O module. And so these all have to be in agreement that that's going to work. And so you have an interfacing part of this transaction and the internal guts of what it's meant to do. And we see all of that happening here. So you have data to and from the environment, and then you have data coming in and from going to the computing system and the internal things that are there. You once again have a buffer. So cache and buffers are once again something that's quite familiar. We'll get into some specifics about what would be the kind of control logic that we would want to have for that. We'll have a couple of specific examples. So there's the International Reference Alphabet, IRA. It used to, term I'm more familiar with is ASCII. So it's American set of characters. And so, but now just to think that, well, the whole world is not America, it's not just us. And so just using some more generic terms is a better way of capturing it. So that's what we have. So it's a basic unit of exchange is the character. And so there can be two types of characters, ones that are printed. So all these ones we're seeing on these charts are printable, but there's also control like carriage return, line feed, and some other things. So those are stuff that we have. So the keyboard codes, when the user depresses a key, it generates an electronic signal that is interpreted by the transducer in the keyboard and translate that bit pattern or the corresponding IRA code. So thus we see this transducer, there's some way of connecting with the external device, moving a mouse, pressing a key, and then it translates it such that it can be loaded into a buffer. and shared with the communication on the computing system. So that's just a little bit of insight on what's going on there. So what are the major functions for an I/O module? They fall into control and timing, processor communication, device communication, data buffering, and error detection. So for control and timing, it coordinates the flow of traffic between internal resources and external devices. For processor communication, it is involved in command decoding, data, status reporting, and address recognition. For device communication, it is involved commands, status information, and data. For data buffering, it performs the needed buffering operations to balance device and memory speeds. And error detection, this detects and reports transmission errors. So here is a block diagram of an I/O module. So we're getting a little bit more specific. And so we have the interface to the system bus. And so this is where we're connecting to where the I/O devices go into the system bus and can communicate with memory and the CPU. So you have registers of various type of data and status control. You have your logic that needs to be configured for it to do one or more specific things. And then you could be connecting with devices. You can be having it connect to one or more device. So you can have it connect to a keyboard and a mouse, and then having configuration information that is passed between those two devices. And so this is the external device facing, and this is the computing system facing side of this block diagram. So we'll go over all three of these. There are three possible techniques for I/O operations. You can have programmed I/O. So you say, go around like a daisy chain. Do you have something to exchange? And it goes around and around and around. You get your certain time where you get a chance to communicate. And then if you don't take it, then you need to be waiting until the next time it comes around for you to be communicating. You can have an interrupt driven. And so this can be more responsive, but it also takes intervention from the CPU to handle that. And then you can have direct memory access where the I/O module and main memory exchange data directly without the processor involved. And so this can actually go faster. I've used this term before. It's a technique, say if you have a slower computer and you're trying to watch a video, it can go directly from the main memory to the monitor and improve the refresh rate and make it more what we're used to by seeing high quality videos. So we have a couple of I/O techniques. And so if there's no interrupt, we can see that programmed I/O is going to fall into that. And then the use of interrupts, we have the interrupt driven I/O, and then we have the direct memory access. And so you could think of maybe this is like a long interrupt. And so once you're done having a large portion of your computing system dedicated to that one thing, then you could be returning back to a general state for doing things in your computing environment. So there are four types of I/O commands that an I/O module may receive when it is addressed by a processor. First is control. It's used to activate a peripheral and tell it what to do. Okay, I'm connected to my keyboard. Now it tells us configuration is your cap lock engaged or something like that, or not. Test, it's used to test the various status conditions associated with an I/O module and its peripherals. You plug in a USB device and say something is not quite right. There's various things in the system that's going to inform you of that. And so that's what we can see in that test mode. Read, it causes the I/O module to obtain an item of data from the peripheral and place it in an internal buffer. And finally, write, it causes the I/O module to take an item of data from the data bus and subsequently transmit that data item to the peripheral. So here just gives you some flow diagrams of how this would work. And so we're seeing the programmed I/O the interrupt-driven I/O and the direct memory access, you can see with the direct memory access, it's quite lean. You're either going to CPU to the DMA, the direct memory access, or back. And so once the direct memory access is activated, it's not going to have to engage with the processor. And so it interrupts the start and informs the CPU when it's done. And so we can see that the programmed IO, we in words kind of walked through this already. There's more steps that need to be activated. And so once it's your turn, after say servicing 10 different individuals, and it keeps coming back to you. So you have 1 in 10 of the 1/10 of the time to do what you would like, or a interrupt, the CPU is going to keep doing whatever it's doing unless it gets interrupts, and it figures out what is the order in which it's going to take care of those things. So with let's think now in terms of the instructions. And so we're programming this input and output part of our computer system. So just like we're going to be talking more as we get into assembly language, we're loading something into a register, taking something out, adding the contents of 2 registers, stuff like that. And towards the end of the class, I'll show you an example for that. With program IO, there is a close correspondence between the IO-related instructions that the processor fetches from memory and the IO commands that the processor issues to an IO module to execute the instructions. So you can read more about this in the textbook, but I also gave you a little bit of a narrative to be thinking about this. So let's think about IO mapping. So we can have memory mapped IO. The device and memory share an address space. The IO looks just like memory read and write. So thus we've translated this information to the way that a CPU does. It communicates with registers, it communicates with memory. And so this can just be like a memory. And so based on whatever those inputs are, it's going to do certain things. There's no special commands for IO. A large section of memory access commands are available. You can also have isolated, so it's a separate address space. You need the IO or memory line selected. So you can have more than one things that are serviced by an address space, and the special command is required for that input and output to take place. And so there's going to be a limited set that would be for that. Here is a figure showing the memory mapped and isolated IO. So this figure contrasts those 2 programmed IO techniques. So for A, the part up here, it shows how the interface for a simple input device such as a terminal keyboard might appear to a programmer using memory mapped IO. So thus we can see we're just seeing a register. We're just looking at the bits, and we do some bit flipping based on what the input and output is. And so that's what we can see there. And for the other one, isolated IO, the IO ports are accessible only by a special IO commands, which activates the IO command lines on the bus. So those are a couple choices here. Then we have interrupt-driven IO. So the problem with programmed IO is that the processor has to wait a long time for the IO module to be ready for either reception or transmission of data. So that has the potential of wasted time and the CPU is not doing anything. So an alternative is to be using this interrupt-driven approach. So the IO module will then interrupt the processor to request service when it is ready to exchange data with a processor. So you raise your hand, you push a button, whatever way you want to be thinking about it, informs the processor that it needs to have some exchange with the processor. So we can see that there is both a hardware part and a software part of the interrupt processing. And so we're going to get a little bit of some idea that programming and what we're doing is not all software. There has to be thought about, well, what is the computing system that we're a part of? And so we can see this with this flow. All those things are things that we need to be aware of and utilizing. So in this figure, we're seeing the changes in memory and registers for an interrupt. And so you get interrupt, everything that was going on in the CPU then has to be stored. You do the interrupt, and then you have to put things back to the way they were before you did the interrupt. And so that's the process that this figure, even still, it can be a little bit complicated to be thinking about it. So once you're interrupt, you have to store your state, service that interrupt, and then reload what was before that interrupt, and then continue on. So there's two design issues that arise because there will be multiple IO modules. How does a processor determine which device issued the interrupt if multiple interrupts have occurred, and how does a processor decide which one to process? So there has to be a unique way of identifying where the interrupt came from, and there needs to be some way of figuring out how important and in what order should I service these things. So there's a couple different ways for device identification. You can have multiple interrupt lines, and so you have direct connectivity through a specific wire or so that goes between the IO module and the processor. You can have software polling, so not only hardware polling where you can poll them one at a time, let's figure that out. You can have daisy chain, and so this is a hardware polling, and so the interrupt acknowledge line is daisy chain through the modules. And finally, you can have a bus arbitration. An IO module first gain control of the bus before it can raise the interrupt line. And so there can be multiple layers of how you go through this protocol of doing an interrupt. So the first thing you have is that you have to get it approved by the system bus, and then the system bus communicates with the CPU. Okay, well, here is a block diagram of a interrupt controller, 8259A. Sometimes when they have this C, this is just another additional information talking about the type of packaging that it is for. So don't really need to worry about that, but some of these following charts, you're going to be seeing that. So C is, say, for a commercial rather than a military or rad-hard kind of, or more robust kind of packaging. So more of a general purpose packaging is what this refers to. And here is a block diagram of an Intel 8255A. So it's a programmable peripheral interface. And we're going to have three charts that are going to be thinking about this. And so you can be seen here that there is the information that's going to and from the system bus. And then we have the information going to and from the peripherals. And we can see that there's three ports, port A, port B, and then port C. And port C is divided into two halves. And in a couple of charts, you'll see that, say, one of these would be dedicated towards managing the keyboard. The other one would be managing the mouse. And then you have, so this would be data exchange, and the other one would be for control and status. This just gives you an illustration of what the packaging would be. So it's a 40-pin device for this chip that would be most likely integrated into your system board or motherboard. Then we get into, well, what specifically for these 8-bit words, what do each one of those bits actually mean? And so we're going to be doing some work with our Mars MIPS emulator, some assembly language, where we're going to be seeing the significance of flipping a bit. And so in each one of these words, they actually do something specific. And so we can be seeing a total of 16 bits are here. A handful of these are not utilized. And so there's a little bit extra that could be built out if there was more capability in a later version that you wanted to have for a chip. And so this just gives you an idea of the interface between this 8255A and a keyboard and a display. And so there's the display mostly is just sending information to the display. So we see information there, but there's also this data check and acknowledge and things like that that goes between them. And a keyboard is mostly going to the processor. So mostly that is the direction that we see going for those types of interface devices. So what are the drawbacks of programmed and interrupt-driven I/O? Both forms suffer from two drawbacks. The I/O transfer rate is limited by the speed by which the processor can test and service a device. So the CPU is going to set the limit there. And two, the processor is tied up in managing an I/O transfer. A number of instructions must be executed for each I/O transfer. When a large volume of data are to be moved, a more efficient technique is direct memory access. And so this is a way of motivating how, hey, maybe we should be having all of these different techniques that are available to us in our toolbox. And this just gives you a block diagram of what this cutting out the processor, and you're going directly from, say, a monitor and your memory. And so this is just giving you a little bit of insight of what that might look like in terms of a block diagram. So here we can see the DMA and interrupt breakpoints during an instruction cycle. And so time is progressing in this direction. And so we have a processor cycle, fetch, decode. Here we can be seeing the DMA breakpoints that were there. So this figure shows where in the instruction cycle, the processor may be suspended. In each case, the processor is suspended just before it needs to use the bus. The DMA module then transfers one word and returns control to the processor. So it can be a fairly agile process that maybe it's not taking all the clock cycles, but it's kind of sharing some of those resources back and forth. The DMA mechanism can be configured in a variety of ways, and some possible ways of doing that are shown here. You can have a single bus and detached direct memory access. You can have a single bus and an integrated DMA I/O, or you can have an I/O bus that could do DMA. And so these are just choices and what would be available for possible ways of doing implementation. So now we're referring to another Intel chip, an 8237. And so that controller interfaces to the Intel chips, the x86 family of processors, and a DRAM memory to provide a direct memory access capability. And so this is just giving you an idea how that would look like. And so once the DMA is activated, you switch off the CPU, and then you're just going directly with this DMA chip. And so this would be another chip that would be on a motherboard or system board to enable us to be able to have direct memory access. So that just gives you a little bit more insight into that. While the DMA is using the buses to transfer data, the processor is idle. And so we've already mentioned that. That's may be an issue. And so, but it's something that we just want to be noting at this point. Okay, the Intel's 8237A has registers, and so we can see that there's these 8 bits that we're focusing on and what they actually do. I'm not going to go into this in detail, but just have you think about, there was an earlier chart that we were briefly showing, giving you a sense of how specific bits can actually be utilized. And so this is where we're getting a chance to see a little bit of that same type of thing here. But now we're showing a table and getting more detailed about what those functions are. And then there's just direct cache access. And so DMA is not able to scale to meet the increasing demand due to dramatic increase in the rates of network IO. So it would be nice if maybe we could try and improve our performance. And so direct cache access is possible. Demand is coming primarily from the high spread deployment of 10 gigabits per second and 100 gigabits per second switches to handle massive amounts of data transfer and to and from database servers and other high performing systems. And so these are huge numbers. For our home, we just recently upgraded to 10 gigabits per second since our internet service provider jumped up to that level. Another source of traffic comes from Wi-Fi in the gigabit range. And so Wi-Fi is slowly getting faster. Wi-Fi 7, it's the latest standard, which it really hasn't gotten to be very popular yet. But here are, I think this might be Wi-Fi 6 or so, some of the data rates that can be done with those types of Wi-Fi devices if everything is just perfect. So the Intel Xeons, Intel's high-end, high-performing processor family uses in servers, high-performing workstations, and supercomputers. So that's what we're getting a chance to see here. Many of the members of the Xeon family use the ring connection system. And so this just gives you this ring. And so you kind of like one at a time, you can be servicing something. And so maybe that would be something that would have utility in those high-end market things. In terms of performance issues, network traffic is transmitted in the form of a sequence of protocol blocks called packets or protocol data units. The lowest or link level protocol is typically Ethernet, so that each arriving and departing block of data consists of an Ethernet packet containing as payload the higher level protocol packet. So there's a lot of details that we can be getting into here. The higher level protocols are usually the internet protocol IP operating on top of the internet, and the transmission control protocol TCP operating on top of the IP. Has anybody ever heard the term TCP IP? Is that, you can give me a thumbs up if you've ever heard that term. It's for some of you that might be interested in networking, that's something that you would be familiar with, and some of you have not heard it, and so that's perfectly fine. It just one of the areas that are out there. So we have network traffic that can be something for us to be thinking about. We talked about the Ethernet, the packets, TCP/IP. The Ethernet payload consists of blocks of data with a TCP header, an IP header. For outgoing data, Ethernet packets are forced in a peripheral component, such as an IO controller or a network interface controller. And for incoming traffic, the IO controller strips off the Ethernet information and delivers the TCP packet to the host CPU. So there's a lot of things that are going on when we're dealing in a network world, and maybe that's a very high way of thinking about this, that when we're sharing and passing information around, that can be something that needs to be navigated. So for both outgoing and incoming traffic, the core, main memory, and cache are all involved. In a DMA scheme, when an application wishes to transmit data, it places the data in an application assigned buffer in main memory. The core transfer this transfers this to a system buffer in main memory and creates the necessary TCP/IP headers, which are also buffered in system memory. So I think I've asked this question, have you ever used a Blu-ray? And even though that's the latest technology for removable media, for playing movies and what have you, I think the number is going down. So having something like we have Apple TV, and so we can actually view movies direct to our TV. And so would be an example of a practical application of this going on. Everything that's going on with the Ethernet layers, it needs to be stripped off. It's just trying to get that information. So we have this direct memory access that's being loaded to our TV, similar to the way that you would be having it in your home. So that's where cache can be helpful. And but we have to be thinking about all of these different protocols that come out into the things that we're thinking about. So packet traffic steps for incoming, we have to be looking at the packet arriving, doing this direct memory access. Is there some type of interrupts that the network interface card is trying to inform us about? We retrieve the descriptors and headers. We have to be able to consider if there's a cache miss, and then we have to slow things down a little bit and find the things that is missing. So thus having a buffer is going to be helpful. Having processing the header, and then finally getting the payload, the actual data that you're looking for. And we can see that there's going to be some reversal of this when we're going outgoing. The packet transfer is requested, the packet is created, the output operation is invoked. We do the direct memory access transfer, so we're going to be having to go out an Ethernet signal. So the network interface card has to be translating and sending those signals, and then the driver frees up the buffer. So once again, we're seeing that what's going underneath the hood is actually a little bit more complicated than we might have thought. So there are details in the textbook about direct cache access strategies. The simplest strategy was implemented as a prototype on a number of Intel Xeon processors back in 2006 and 2010. More substantial gains can be realized by avoiding the system buffer and main memory altogether. So you're trying to streamline and not have to go as farther and farther into a computing system, and that can help out with performance. Okay, I'm going to skip over some of this for the sake of time, and just for some of you, this may be the first time that you've got a chance to encounter this, and so give me a chance just to do a little scanning here. Okay, all right, I'm going to skip over to over that, and the last part of the lecture and this chapter deals about different types of input and out devices. And so I think everybody here is familiar with USB. Anybody, you guys all familiar with USB? Thumbs up if you know about that. Probably you're at this point, you're using it all the time. And so these various upgrades, it used to be just USB 1.0, 2.0, 3.0, 3.1 as of the writing of this textbook. And so it's a serial connection, and it can do some high-speed input and output up to 9.7 gigabits as of the USB 3.1 standard. So you guys are familiar with this. Most likely your keyboard and mouse connects to your computer through that. If you have a desktop, now that there's a lot more laptops versus desktops, maybe you don't have it. This is something that's I don't think is really widely used anymore. I know Apple was configuring it and using it on devices, say roughly about 10 years ago. But at the time, it could actually do some fairly fast connectivity things, but this is another serial device that you could be connecting with. SCSI, a small computer system interfaces. Some hard drives used to have a SCSI interface. And so this is another legacy thing that's out there. Thunderbolt. How many people have Thunderbolt on your computer or tablet? Anybody have a Thunderbolt connection? If you got a Mac, most likely you do, and it's now starting to get involved in various PC configurations. I have a tablet, a Microsoft Surface, and unfortunately it doesn't have Thunderbolt, but it does have USB 3.1. The thing that can make it a little bit difficult to discern what's going on is because they have the same connector. So this was developed by Intel with collaboration from Apple. So Apple deployed them first, but now it's gotten to be this quite useful standard. And also another thing with USB-C and also with the Thunderbolt, you also get charging as well as the data exchange. InfiniBand, it's an I/O specification aimed at the high-end server market. And so it's been around for about 25 years. I'm not going to get into this a little bit because we're not really focused too much on the server part of computer systems, but it's a switch-based architecture that can connect up to 64,000 server storage systems and network devices. And so we'll see this in some of the diagrams that we'll be going through as we go through our course. Well, here's another interface. And I'm going to show you a couple of SATA interfaces, a serial advanced technology attachment. We already talked about the PCI Express, and I showed you an actual a device that could plug into your motherboard and then give you the SATA access and give high-speed connectivity and actually have more hard drives configure in your computing system. Ethernet, this is still the fastest way to get connected to the internet. Ethernet is faster than Wi-Fi. And so up to 100 gigabits per second. And so that's extremely fast. Still not something that's available in the commercial market. The commercial market is now somewhere between 1 and 10 gigabits, being something that's fairly common. But that's something that you all will want to make sure that you're familiar with. So here, the Wi-Fi, this is, they're referring to the IEEE 802.11ac, and I think this is the Wi-Fi 6. I think it may be the Wi-Fi 6 standard. I think the AX is the Wi-Fi 6. Forgot what the acronym that it has after that, this 6A or 6 or something like that. And then there's the Wi-Fi 7. So this continues to be going higher, and to radiate at these frequencies, there's always a spectrum issue that needs to be worked out to go from this. And so Wi-Fi 6 and lower, it uses 2.4 and 5 gigahertz. Now with Wi-Fi 6 plus, Wi-Fi 7, they also introduced using the 6 gigahertz as another area that they radiate their signals. This is just an illustration of the IBM Z13 I/O channel structure. And so this just gets into more complex things that are available for a server. And I'm not going to dwell on this at this point. I think we've covered a lot for our lecture today. And finally, this is just another diagram talking about this Z13. Okay, well, we did a quick tour of a lot of things about inputs and outputs, including the external interconnection standards. I'm thinking of USB, Ethernet, Wi-Fi. Those are probably the ones that you'll be using the most. And we have these various choices of how we can have our I/O devices connecting to our computing system, but it is important that we get our computing system connected. let me just do around the room. Any comments or questions or thumbs up if you're tracking this at a survey level of getting a chance to get a better sense of what's going on with IO devices. Okay, good. Let me do show and tell for a minute. I'll stop sharing my screen and I'll pull out a couple of hard drives. And so I mentioned this quickly, but I know people may not have picked this up. This is a SATA hard drive by Seagate. I've had really good customer service experience with Seagate. And it is a SATA interface. This is a 3.5-inch hard drive. And you can see on the back, you can see this is where the platters rotate around the spindle. And so that's where you can see that on the back. This is not hermetically sealed. It's not like what I was showing on Tuesday, where it has helium. And so this actually just has air going in and out of the hard drive. And it's probably going to be really hard for you to see, but these are the two connections. One is the power and one is the actual SATA connection. So the smaller connector is actually the SATA connection for that hard drive. So that's a 3.5-inch. This is a 2.5 inch. So this would be the hard drive that you would have in a laptop, for example. And you can see this the same kind of configuration on the back. A spindle. The platters have to be smaller, so you're constrained in size. So it's more difficult to get the size of the hard drive to be the same for the 3.5-inch form factor. And so you can be seeing those same connectors. They're exactly the same. And so if I wanted to, I could either have a 3.5-inch or a 2.5-inch put into whatever computing device I would like. It just may not have the right kind of carriers to put it in. So, but that's gives you a little bit of a sense of what that would look like. I'll show you some pictures, not today, of an SSD. The ones that I have are in my computer and I don't have any extra ones, so I won't be showing you an illustration of that. Any other questions that folks have before I move on? I'm gonna
Those
next,
are HDDs, right?
yes,
Those are HDDs?
yes, HD.
Okay. All right. Thank you.
Okay, I'm going to pull up a couple of things here. So this is I'm actually have with remote desktop connection, RDC. Microsoft has a program to do this. I actually am hooked in from my Mac to see my laptop, I'm sorry, my tablet. And I mentioned this before, but Windows, Microsoft does now have support for both the x86 type of processors as well as the ARM-based processors. See, this is a 64-bit ARM processor made by Microsoft. And what you'll find is that there is a fair amount of overlap, that it runs seamlessly with the same software that you would see in a regular x86 type of Windows machine. So some of you have Windows, some of you have Apple products, and so I wanted to at least give a chance to give a little bit of a sense of that. Another thing that I wanted to share is we're going to next go into this assembly language emulator. And so this is the Mars program. And so I'd recommend that you fire it up. And so it's literally the same way that once you have Java installed or Open Java, you just double click on this and it's going to come up. And this is what the interface looks like for on a PC. You can see that the GUI is more or less the same, but it has a little bit of a slightly different look and feel. And so I'm gonna pull up the version that you have available, the default for on a Mac. And so this is what I would like to be focusing on next. So if you all wouldn't mind opening up your Mars MIPS emulator, does everybody, why don't you just do a thumbs up if you've got that up and running, and I'll walk you through this one program. And this will be starting to give you some insight of what's going on doing an assembly language program. Okay, got some folks acknowledging that they have it up and running. So what this program does, it's going to showcase a couple of things. It's going to be showcasing different ways that you can be getting information into registers. It's going to do an add, a subtract. It's going to read from a memory and load it into a register. And then when it's finally done, it's going to load and store information into a memory location. So this is the guts of what's going on here. There are a couple of directives, .global, .text, and we have .data, and then we have this .word that talks about the type of information that's being put into this this memory location. And so those are some maybe constructs in terms of programming. Some of this may be new for you. So once again, if you go up to the help, this program is getting dated, but it's still fairly good in terms of it all being self-contained. And so that's one of the reasons why I still have us use it. So here we can see all of the different commands, well, at least most of them, as I mentioned before. There are a couple other, like the syscall, I wasn't finding the li command, but this just gives you another load information that's related to doing syscalls. And so let's just walk through this program as an example. And this would be an example of the kind of thing that you would want to be writing for your assembly language programs. We'll have some chapters where we're going to be talking about the what it means to have an instruction set. So here we'll be talking about that in a couple of weeks. So this is a little bit of a precursor for that, but I just wanted to try and give you some heads up so that when you start to use this emulator, it's not going to be so unfamiliar. So you have a global here, so main, and so those that are familiar with programming in Java, and so thus having a main is something that you want to have. All program code is placed after the .text, and so here we have okay, we have a main, and then here after the .text, this is where we put in the information. So here is the main. So this is the beginning of the actual lines of code. And so here we're going to be load immediate the value of 25 into this register 2. So let me go ahead and execute, compile this. Wrong button. And so if I was to go back and forth, you can see this is how it would look like here. This is getting even closer to how the computer looks at this. And you can see there's a couple examples that one command line actually turns into 2 command lines when it goes through this processor. And we're going to single step through this, and you can see some of this happening. So the single step here is this green arrow, but it has a 1 by it. So the first thing that we're going to do is we're going to be loading load the value of 25 into register T2. So if I just click that, now I see the value of 25 is in this register T2. So that's the first command that we have. It also highlights going to the next command. Now we're going to load the word stored in value. So here we can see the value is one of these things down here. Value is 12. So it's going to load the word stored in value. And so the first thing it has here is going to get the information for the address that needs to be getting this information from. Okay, now it knows the memory location, and then it's going to actually load this. We want to be loading this into register T3. So click on the second part. Now we have that, the original 25, we have the 12. The next command is we're going to be adding T2 and T3 and putting in T4. So we have values in T2 and T3. Do a single step. Now 37 is the addition of those two. We see that has been done. And then we're going to be doing a subtract. We're going to subtract T2 and T3. So we're going to be subtracting T3 from T2 and put it into T5. And so just single step on that. We can see there is the difference of those two numbers. Now we want to be storing that into Z. Remember, Z is this other location. It's initialized to a value of 0. Now we're going to be storing the value in T5, 13, into Z. So this is broken down into two parts, getting the memory location and then storing it into the memory location. So that's the first part, the memory location, and then it stores it into that memory location. And then finally, we're doing a clean exit. We're going to have this directive. So we go to directives. Just a second. Sorry, syscalls. And we're going to be loading 10, and this is a terminate. So we're going to have a clean terminate when we do this last command here. So we execute that. First, we load the information of what syscall we're doing. Get that. And that's here loaded in the register. And we finally we execute that. And then it says program is finished running. Any questions on what I just showed you with a sample program that we have using the MIPS type of the ARM-based type of assembly language rather than the Intel-based assembly language? Give me a thumbs up if you guys are tracking what I have here. Okay. Yeah, couple folks are good. You're starting to see what we're putting together. So you can see after looking at this, maybe it seems a little bit intimidating, but just when you start to break it down, it's just a little bit lower type of programming, but it's still the kind of things that we are familiar with doing. And so keep that in mind, okay? All right, well, I think that's what I wanted to share for today. Any other comments or questions that anybody has?
I just had a question.
Okay, Nathan?
So for this MIPS programming, so like how does that, like based on like when we're building like for based on our theme of the project, how do we apply that? How do we, when we program it, how do we apply to it? Like, how does that? I'm trying to get
Okay,
an understanding of like the MIPS programming because I'm not sure like still like how it's supposed to be worked on.
this is what I would have you focus on, this putting things, doing an evaluation on registers. This would be the kind of thing that I would have you focusing on. So you could be doing some of the commands you can do logical and so you could be doing an and of 3 registers, an or. Those would be things that you could be doing as an example. Or so that would be where I'd have you focus on trying to think about the relationship between this. And so remember that what I was saying is I wanted to have folks have a minimum of 3 inputs for your digital logic.
Yeah.
You can have the same thing, that you can have a minimum number of 3 inputs that you're going to be doing some aggregation of that based on what you want to do. Okay, does that help?
Yeah.
Nathan?
Are we gonna talk more about this like later on? Because like this is like really new to me, so it's like
Yeah,
you know.
this is a first introduction of going through this.
Okay.
It's not the only one. So don't worry, we're gonna keep going over this, okay?
All right. Thank you.
All right. Well, everybody have a wonderful day, and I'll look forward to seeing you next Tuesday. God bless.
Thank you, Professor.
Sure thing.
Thank you.
Professor,